Draw the boundaries of your code. Hey everyone, and welcome. In today's explainer, we're going to explore the ultimate security gates of object-oriented programming, or OOP. We are talking all about access modifiers. Whenever you build software, you have to make some pretty crucial decisions right off the bat. What data should be wide open to the public, and what needs to stay completely hidden? Well, by the end of this explainer, you're going to understand exactly how keywords like public, private, and protected actually work, and how to use encapsulation to shield your data from absolute disaster. So, let's dive right in. Here's a quick look at our roadmap for today. First, 1, the boundaries of code, followed by 2, encapsulation, shielding your data. Then we'll break down the specific modifiers, so 3, public, the open doors, and 4, private, the secret vault. After that, we'll cover 5, protected and default access, and finally, we'll wrap it all up with 6, the bank account analogy. All right, let's kick things off with section 1, the boundaries of code, setting the rules of the game. So, I really want you to think about this question for a second. Who actually gets to see your data? When you're building a program, your code isn't just floating around in a vacuum, right? Different parts of your system are constantly interacting, and a lot of times, entirely external systems are trying to interact with your code too. If you don't set strict boundaries, any part of your program could just change any piece of data at any time. Imagine the vulnerabilities, the bugs, and just the absolute chaos of unauthorized access. No thanks. To put that into perspective, think of your code like a house. Object-oriented programming is all about modeling code after real-world things. And just like a physical home needs doors, walls, and locks, your code absolutely needs access levels. Your living room? That's public. Anyone you invite inside can sit there. The family room is protected, shared only with your close relatives. But your personal safe hidden in the back? That's private. Only you have the combination. And honestly, this is exactly how we need to structure our software. Moving on to section 2, encapsulation, shielding your data. Now that we have that house visual in our heads, let's talk about the actual technical engine that makes these boundaries possible. Encapsulation is literally one of the 4 foundational pillars of OOP. Basically, it means grouping your data, your attributes, and your methods together inside a class, while strictly restricting direct access to that data from the outside. It's like putting a protective force field around your variables. Why? Because you want to stop external code from making uncontrolled, super dangerous changes to your core data. You're forcing everything to go through approved, safe channels. Which brings us to section 3, public, the open doors. The public keyword is the widest, most open access level you can possibly use. If you label a class, a variable, or a method as public, you're essentially saying, hey, 0 restrictions. It can be accessed and triggered from absolutely anywhere in your entire program. Remember our house analogy? This is the wide open front door. Now, you might be wondering, if it's so open, when do we actually want to use public? Well, while it's super dangerous for sensitive data, for behaviors, meaning your methods, it is essential. The best uses for public access are the actions you explicitly want the outside world to use. We're talking about things like a login method, a register function, a deposit action for an account, or show info. These are your system's public interfaces. They're literally meant to be interacted with. But what about the stuff we definitely do not want people messing with? Section 4, private, the secret vault. Okay, so this is the complete opposite end of the spectrum. Private is the absolute most restricted access level you can apply. If a variable or method is marked private, it is securely locked inside its class. End of story. Absolutely no outside class, no external system, no other part of the program can see it or touch it. If they even try, the system will just throw an error. This is exactly where you stash your passwords, your bank balances, and your most critical logic. But wait, if the data is locked away, how do we actually use it? Good question. We use a very specific controlled process called getters and setters. Here's how it works. Step 1, you define your sensitive data as private. Step 2, if outside code legitimately needs to read that data, you create a public getter method. All it does is return the value without letting anyone change it. Step 3, if the data actually needs to be updated, you create a public setter method. And here's the real magic. That setter can include built-in validation logic to make absolutely sure the new data is safe before applying it. It's really important to grasp the vital difference here. With public access, you're dealing with direct, uncontrolled data manipulation. Anyone can just change a variable to anything at any time. It's incredibly risky. But with private access, You have controlled interaction. You literally force the outside world to ask for permission via a method, and that method validates the request. It's the difference between letting someone just stroll directly into a bank vault versus making them hand their request to a teller at the front desk. Section 5, Protected and Default Access, finding that middle ground. So, we've seen the extremes, right? Public and private. Now let's look at the nuances. First up is protected. Think back to the family room analogy. Protected access means the data or method is accessible to anything within the same package, but, and this is key, it is inherited by subclasses. So even if a subclass lives in a completely different package, it still gets access to the protected members of its parent class. It is perfect for when you're using inheritance and want to share core functionality strictly with derived classes, but keep it hidden from the rest of the world. Next is default access, which you'll sometimes hear called package private. This is what happens in languages like Java when you just don't type an access modifier at all. So what actually happens? Well, the code just defaults to a local neighborhood watch. It becomes accessible only to classes strictly within the exact same package. If a class in a different package tries to reach in, nope. Access denied. Okay, I highly recommend pausing and taking a mental picture of this matrix, or even a screenshot. It perfectly summarizes everything we just covered. Think about it this way. Private gets a yes only in the same class. Default expands that to a yes in same class and same package. Protected goes a step further, same class, same package, and subclasses. And public? Well, that's just a yes across the board, everywhere. Honestly, keeping this matrix in the back of your head is going to save you countless hours of debugging. Finally, Section 6, the bank account analogy. Time to see this in action. Let's map all these mechanics to a real-life coding application to really cement why it matters. Imagine you're coding the user profile for a banking app and you decide to make the user's balance public. Guys, this is a massive architectural flaw. Because it's public, any external code anywhere in the app can just write a line of code saying balance equals -5,000. No checks, no balances, no validation whatsoever. A single typo or a malicious script could instantly wipe out a user's funds or put them in massive, totally illogical debt. And this brilliantly illustrates the fix. Encapsulation completely solves this problem. Without it, a rogue -5,000 goes right through, ruining the data and probably crashing your whole system logic. But by making the balance private, the only way to interact with it is through the public deposit method. So, if a bug or a user tries to pass -5,000 into the deposit method, the internal logic catches it, says, wait, you can't deposit a negative number, and safely throws an error. The system rejects the invalid data and the balance stays perfectly safe. Boom. So let's wrap this up and summarize the core benefits here. Why does encapsulation, powered by these access modifiers, actually matter so much? Well, first, it secures critical data from unauthorized access. Second, it enforces logical rules, like, preventing negative bank balances. Third, it really simplifies code maintenance because you know exactly where a variable is allowed to be changed. And finally, it prevents accidental breaks, especially in huge projects where you have multiple developers working on the exact same code base. I want to leave you with this final thought as you head back to your own projects today. If your code was a bank, how easily could someone empty the vault? Take a really hard look at your architecture, lock down those variables, set up your public getters and setters, and draw firm, unbreakable boundaries around your data. Thanks so much for joining me on this explainer, and I'll see you in the next one.